In September of 2024, astronomers watching the interstellar object 3I, Atlas noticed something that made absolutely no sense. The way it was reflecting sunlight, the angle, the intensity, the wavelength distribution, it didn't match what they were looking at. It couldn't match. The geometry was impossible. And yet there it was, captured by multiple independent observatories, consistent across weeks of observation. 3I, Atlas was reflecting light at the wrong angle, and in astronomy, when light behaves in ways it shouldn't, it means you're looking at something you fundamentally misunderstood. To understand why this matters, we need to talk about something that sounds simple but is actually one of the most powerful tools in astronomy: reflected light. Everything we know about objects in our solar system, asteroids, comets, moons, even the planets themselves, comes down to how they reflect the sun's light back to us. It's basic physics. Light hits an object, bounces off at predictable angles, and we capture that reflection with our telescopes. From that reflected light, we can determine what something is made of, how it's shaped, how it's rotating, even its surface texture. It's a technique so fundamental, so reliable, that we barely think about it anymore, until it doesn't work. The science of light reflection goes back centuries. In the 1600s, scientists like Christian Huygens and Isaac Newton were already working out the mathematics of how light behaves when it encounters different materials. They established principles that still hold true today. Smooth surfaces create specular reflection, where light bounces off at equal angles like a mirror. Rough surfaces create diffuse reflection, scattering light in many directions. The ratio between the two tells you about surface texture. The wavelengths that get absorbed versus reflected tell you about composition. It's elegant, it's predictable, it works. By the 20th century, astronomers had refined these techniques to extraordinary precision. They could look at the light curve of an asteroid, the way its brightness changed over time, and reconstruct its shape and rotation period. They could analyze the spectrum of reflected light and identify specific minerals on the surface. When the first interstellar object, Oumuamua, was discovered in 2017, one of the first things astronomers did was analyze its reflected light. The results were puzzling. Oumuamua was tumbling chaotically, and its light curve suggested an extremely elongated shape, something like a cigar or a pancake. The reflection patterns were unusual but not impossible, just odd. Then came 2I Borisov in 2019, and the reflected light made perfect sense. It was a comet. The light showed exactly what you'd expect from a comet: a nucleus surrounded by a coma of gas and dust, scattering light in predictable ways. The spectrum revealed familiar materials: water ice, carbon compounds, the usual suspects. Borisov was comprehensible. It followed the rules. When 3I Atlas was discovered in early 2024, astronomers assumed they'd be able to do the same thing: point telescopes at it, measure the reflected light, figure out what it was made of and how it was shaped. Standard procedure, routine analysis. Except it wasn't routine, not even close. The first odd readings came in March of 2024, about a month after 3I Atlas was discovered. Astronomers were collecting photometric data, measuring how bright the object appeared over time as it tumbled through space. Every asteroid and comet has a light curve, a pattern of brightening and dimming caused by rotation. As different faces of the object point toward the sun and toward Earth, the amount of reflected light changes. A perfectly spherical object would have a flat light curve because it looks the same from every angle. An irregular object, which most asteroids and comets are, shows periodic variations. More surface area facing you means more reflected light, simple geometry. The light curve of 3I Atlas was showing variations, which was expected, but the pattern didn't make sense. The brightness was changing, but not in the smooth, periodic way it should. There were irregularities, sudden brightening events that didn't correspond to any reasonable rotation model. Some observations showed the object much brighter than it should be, based on its estimated size and distance. Other observations, taken just hours later from different observatories, showed it dimmer than predicted. At first, this was chalked up to observational error. Maybe different telescopes were using different filters. Maybe atmospheric conditions were affecting the measurements. Maybe the object was outgassing unevenly, creating temporary bright spots. By April, with more data coming in, the problem persisted. Multiple observatories using different instruments and different observing techniques were all seeing the same inconsistencies. The light curve wasn't just irregular, it was geometrically impossible. When you account for the object's position relative to the sun and relative to Earth, when you calculate the phase angle, the angle between the sun, the object, and the observer, the amount of light being reflected didn't match any known scattering model. It was as if 3i Atlas was somehow reflecting light from directions it couldn't possibly be receiving it from. Some astronomers proposed that the object might have an extremely unusual shape, something so irregular that it was creating unexpected reflection patterns. But even the most extreme shapes, long, thin needles, flat disks, fractal structures, couldn't explain what was being observed. Others suggested the surface might have properties we'd never encountered before. Maybe it was highly reflective in some areas and highly absorptive in others, creating a patchwork that caused the strange variations. But spectroscopic analysis didn't support this. The spectrum looked relatively uniform, consistent with a typical cometary composition. Then, in late May, a team at the European Southern Observatory made a discovery that changed the conversation entirely. They had been tracking 3i Atlas with high-precision astrometry, measuring its exact position against background stars. When they compared the visual position of the brightness peak, the brightest point of reflected light, with the calculated position of the object's center of mass based on its trajectory, they didn't match. The light was coming from a point in space offset from where the object actually was. Not by much, just a few arcseconds, but consistently, measurably offset. The object was in one place. The reflected light was brightest in another place. That shouldn't be possible. Let's break down what it means for light to reflect at the wrong angle, because this gets to the heart of some very fundamental physics. When light from the sun hits an object in space, it interacts with the surface in predictable ways governed by the laws of optics. The angle of incidence, the angle at which light hits the surface, determines the angle of reflection. For a smooth, mirror-like surface, these angles are equal, measured from the perpendicular to the surface. This is specular reflection, the kind you see in a mirror or on calm water. For a rough surface, which most astronomical objects have, the light scatters in many directions, creating diffuse reflection. But even diffuse reflection follows statistical rules. Most of the light bounces back in the general direction it came from. This is called backscatter, and it's why a full moon looks brighter than a half moon even though you're seeing the same amount of illuminated surface area. Now, here's the critical part. The direction light reflects depends entirely on the local geometry of the surface where it hits. If you know the shape of an object and you know where the sun is relative to that object, you can calculate, with high precision, where the reflected light will go. And if you're observing from Earth, you can predict how bright the object will appear based on how much of that reflected light is directed toward you. This is basic ray tracing, the same mathematics used in computer graphics to render realistic images. It works. We use it to model the appearance of asteroids, to predict the brightness of comets, to analyze the surfaces of planets. It's not controversial science, it's textbook physics. What was happening with 3i Atlas violated this. The brightness distribution, the pattern of where light was reflecting from the object's surface, didn't correspond to the surface geometry that should exist based on the object's overall shape and orientation. Imagine holding a ball and shining a flashlight on it. The brightest spot is always where the light hits most directly, perpendicular to the surface. Now imagine the brightest spot appears somewhere else, off to the side, where the light is hitting at a glancing angle. That's what 3i Atlas was doing. The peak brightness was appearing at the wrong place on the object. Some researchers initially thought this might be explained by a highly non-uniform surface. Picture an asteroid covered in boulders, or a comet with jets of gas erupting from specific vents. Local features can create localized bright spots. But even accounting for this, the geometry didn't work. The offset was too consistent, too systematic. It persisted across different observation angles as the object rotated and as Earth's position changed. Whatever was causing this, it wasn't just a surface feature. It was something fundamental about how the entire object was interacting with light. Another possibility was that the object wasn't a single solid body, but rather a collection of fragments, a rubble pile held together by weak gravity, with the fragments separated by enough space to create complex light scattering between them. Light could bounce between fragments, creating secondary reflections that might appear to come from unexpected angles. This is called multiple scattering, and it happens in dense particle clouds like cometary comae. But 3I Atlas didn't have a dense enough coma to explain the magnitude of the effect being observed. The coma was relatively thin, and most of the light was clearly coming from the solid nucleus, not from scattered dust. The astronomical community was divided. Some maintained that the observations had to be flawed somehow. Systematic errors in the photometry, incorrect assumptions about the object's distance or velocity, something. The idea that an object could consistently reflect light at geometrically impossible angles challenged fundamental principles. It suggested either our understanding of optics was wrong, which seemed absurd, or something very strange was happening with this particular object. Others took the data at face value and began proposing increasingly exotic explanations. Maybe the object had a highly unusual crystalline structure that was refracting light through internal pathways before it exited the surface. Maybe it was covered in ice crystals oriented in some specific way that created coherent scattering, like the ice halos you see around the sun on cold days. Maybe, and this was the really speculative end, the object had some kind of organized structure we didn't understand. The breakthrough came in July, and it came from an unexpected direction. A graduate student at MIT analyzing archival data from a completely different survey noticed something about the rotation of 3I Atlas. The object wasn't just tumbling randomly, it had two distinct rotation periods, a fast rotation about 8 hours and a much slower precession about 63 hours. This is called non-principal axis rotation, and it's actually not that uncommon in asteroids, especially irregularly shaped ones or ones that have experienced collisions. The object spins around one axis, while that axis itself wobbles around a second axis, like a football tumbling end over end while also spiraling. But here's what made this important. When the student plugged these two rotation periods into a detailed light scattering model and accounted for the changing geometry as the object tumbled, something clicked. The apparent displacement of the brightness peak, the wrong angle reflections, they could be explained if the object had a very specific shape. Not just irregular, but bifurcated. A contact binary. Two lobes connected by a narrow neck, tumbling in such a way that at certain orientations, light was reflecting off one lobe while the center of mass was located in the other lobe. The geometry finally made sense. This was confirmed in August when high-resolution radar observations from the Arecibo successor facility in Puerto Rico managed to get a return signal from 3I Atlas. The radar data clearly showed a double-lobed structure, two distinct masses in contact, rotating around their common center. The larger lobe was roughly 120 meters across, the smaller about 70 meters, connected by a narrow bridge of material maybe 20 meters wide. When you're observing such an object from a distance, your telescope can't resolve the two lobes separately. You see a single point of light. But the light is predominantly reflecting from whichever lobe is oriented most favorably toward the sun, while the object's center of mass, the point around which it's gravitationally balanced, is somewhere between the two lobes. This creates an apparent offset. The light source and the gravitational center don't coincide. With the contact binary structure confirmed, everything started to make sense. The irregular light curve, the sudden brightening events, the geometrically confusing reflection angles, all of it could be explained by the complex tumbling of this dumbbell-shaped object. As it rotated, different faces of the two lobes would catch sunlight at different times, creating unpredictable variations in brightness. When both lobes were oriented to reflect light toward Earth, the object appeared much brighter than its size would suggest. When the neck region was facing us, presenting minimal surface area, it appeared dimmer. But the story didn't end there, because the existence of a contact binary raised new questions. How did this structure form? Contact binaries are common in the asteroid belt. We see them frequently. They're thought to form from gentle collisions between objects or from the gradual deformation of rubble pile asteroids due to rotation and tidal forces. But 3I Atlas was interstellar. It didn't form in our solar system, it came from somewhere else, somewhere with potentially different formation conditions, different collision histories, different environmental factors. The analysis of the radar data revealed something else intriguing. The surface properties of the two lobes appeared to be different. One lobe had a rougher surface texture, scattering light more diffusely. The other had smoother areas, possibly ice patches, that created more specular reflections. This asymmetry explains some of the more extreme brightness variations. Depending on which lobe was facing the sun and which was facing Earth, the reflective properties changed dramatically. It was like the object had two different faces, each with its own personality. By September, papers were being published analyzing every aspect of 3I Atlas's structure and behavior. The consensus was emerging that this wasn't just a contact binary, but specifically a primordial one, meaning the two lobes had been in contact for a very long time, possibly since the object's formation billions of years ago. This was based on the smooth connection between the lobes, the lack of sharp collision features, and the uniform composition across both sections. Whatever process created this object, it happened early in the history of some distant planetary system, and the configuration had remained stable across incomprehensible spans of time and distance. So why was 3I Atlas reflecting light at the wrong angle? The answer, in the end, was geometry, pure and simple. But not the geometry we expected. We were treating the object as a single body, calculating light reflection based on a single center of mass and a single rotation axis. But it wasn't single, it was dual. Two objects sharing space, sharing motion, but reflecting light independently. The peaks of brightness were coming from whichever lobe was optimally positioned, but our calculations were referencing the combined center of mass. The light was reflecting at exactly the right angle. We were just measuring from the wrong point. This is a perfect example of how assumptions shape observation. Every astronomer analyzing 3I Atlas was, consciously or unconsciously, assuming they were looking at a single solid object. This assumption is so fundamental, so deeply embedded in how we think about asteroids and comets, that it didn't even register as an assumption. It was just background reality. And because of that assumption, the data looked wrong, the reflections looked impossible, the geometry looked broken. But the data wasn't wrong. Our mental model was. There's also a technical element here that matters. The resolution of our telescopes, even the best ones, isn't sufficient to visually separate the two lobes of 3I Atlas at the distance it was observed. We were seeing a single blurred point of light. The only way to detect the binary nature was through indirect methods like radar, or through careful analysis of how that point of light behaved over time. This is a limitation we run into constantly in astronomy. We're trying to understand the detailed structure of objects we can barely see, using only the light they emit or reflect. It's like trying to understand the architecture of a building by looking at it from 10 miles away through fog. You can make inferences, but you can easily be wrong about fundamental aspects. The fact that it took months to figure this out, despite observations from dozens of professional observatories, tells you how subtle the clues were. The offset between the brightness peak and the calculated position was only a few arcseconds. That's tiny. It's the apparent size of a coin viewed from several kilometers away. If the observations had been even slightly less precise, if the object had been slightly more distant, if we'd had fewer data points, we might never have noticed the discrepancy. 3I Atlas would have remained a puzzling interstellar object with weird light curves, and we'd have moved on, cataloging it as just another anomaly in a universe full of anomalies. 3I Atlas is still out there, tumbling through space on its long journey back to interstellar darkness. The two lobes continue their ancient dance, spinning and wobbling in patterns established eons ago. The light still reflects at what we initially thought was the wrong angle, though now we understand it's exactly the right angle just from an unexpected place. The object hasn't changed, only our understanding has. This episode highlights something important about the scientific process. We don't just observe nature objectively and neutrally. We observe it through frameworks, through models, through assumptions about how things work. Most of the time, those frameworks are correct, or correct enough. They let us make sense of the flood of data coming from telescopes and instruments. They let us distinguish signal from noise, pattern from randomness. But sometimes those same frameworks blind us. They make us see impossibilities where there are only misunderstandings. The beauty of science, though, is that it's self-correcting. When enough anomalies pile up, when the data refuses to fit the model no matter how you massage it, eventually someone questions the assumptions. Someone looks at the problem from a different angle, literally in this case, and finds the explanation that makes everything click into place. The moment of realization, when confusion resolves into clarity, when the impossible becomes obvious in hindsight, that's one of the most satisfying experiences in research. 3i Atlas also reminds us that the universe is under no obligation to conform to our categories. We have boxes labeled asteroid and comet and contact binary and rubble pile, and we try to sort every object we discover into one of these boxes. But the universe doesn't know about our boxes. It just makes things according to the laws of physics, chemistry, and chance. Sometimes those things fit our categories neatly, sometimes they don't. And the ones that don't, the edge cases, the anomalies, those are often the most informative. We'll encounter more objects like 3i Atlas. The next generation of survey telescopes will detect interstellar visitors regularly, maybe dozens per year. Each one will teach us something about the diversity of small bodies in the galaxy, about formation processes in distant stellar systems, about the range of structures and compositions that physics allows. Some will be familiar, some will be strange, and some, like 3i Atlas, will seem to break the rules until we realize we were applying the wrong rules to begin with. The light was never reflecting at the wrong angle, we were just looking at it wrong. And that's a lesson worth remembering every time we encounter something that doesn't make sense. Before declaring the universe impossible, check your assumptions. The answer is usually simpler than you think, but stranger than you expected. 3i Atlas proved that. A simple binary object, tumbling through space, reflecting light exactly as physics demands, and yet puzzling astronomers for months because we couldn't see what was right in front of us. Or rather, what was separated by a narrow neck of ancient ice and rock, tumbling together through the cosmic void, reflecting starlight at precisely the angles geometry requires.